ההרצאה השנייה, היום ההרצאה תהיה של שי על דוקר אינטרנלס, זה לא על איך משתמשים בדוקר, זה על אשכרה איך דוקר עובד, הולך להיות מאוד מעניין, שווה להישאר, וגם עם החברים שלכם שלא הגיעו, שרוצים לדעת איך עובד דוקר, כדאי לכם לבוא. יש לנו עוד הרבה בקנה, הרצאה היא פעם בחודש, אנחנו עושים כרגע הרצאות, מוזמנים. שי, תודה רבה.
Okay, we'll conduct the talk in English for the English speakers. So first of all, nice to meet you. My name is Shai Ben Shalom. I'm a software developer in the platform group, more specifically in the deployment and runtime team. And as a team, we are responsible for everything that is happening from the moment you go into Santa and deploy your application, and up to the moment that your application is running on the cloud, on an EC2 instance, on AWS. And as a result, we are dealing a lot with containers and more specifically with Docker. And we are going to talk a lot about Docker today. But before diving in to the tech details, I want to introduce you a simple use case and ask a question. So suppose you are users that have an Ubuntu machine and you are typing the following command: docker run -it debian echo hello Appsflyer. And my question to you is, what is going to happen next? Not what, okay. What will happen after typing the above command? No, wrong, wrong answer. Better answer than that? Someone? So, no, well, the answer is pretty simple. I'm disappointed that you didn't know. A new container will be created. And what will the container do? The container will run the command hello Appsflyer on a Debian virtualized operating system. And while this seems pretty straightforward, and I guess most of you ran this command many times and seems like trivial to you, for me as a software developer starting to use Docker a few years ago, it was like a black magic. Because think about it, you can run on a Linux machine and get a whole complete different distribution of Linux. You can run on a Mac and receive an Ubuntu machine in a matter of seconds. And for me, it's amazing. And again, it's like a black magic. And my goal in this talk will be to try to explain you what this black magic actually is. Spoiler, this is not really a black magic. This is operating system abilities, but it is amazing. And let's start by describing the agenda for today. So I divided the talk into three parts. On the first part, we'll speak about the container fundamentals. The second part will mainly focus on the Docker internals. And on the third part, we'll be talking about the Docker high-level architecture. It will not be an hands-on talk. It will be more like a theoretical talk on how things operate behind the scenes. So let's go on. Can someone just mute the microphone? Okay. So let's begin with the first part, which is the containers fundamentals. And I want to ask you this: what is a container? Does anyone know? A process. This is partly correct. Can anyone? Process that consists of C group, correct. This is the more advanced answer, right? Can anyone give another answer, more accurate answer? Okay. So I will give the full answer. A container is just a set of one, maybe more processes that are isolated from the rest of the system. Remember, container is not like a Linux term. It's, in the end of the day, a process, maybe more than a process, as some of you mentioned. So we said that this is a process that is isolated from the rest of the system. Does anyone know how do we achieve this isolation? Namespaces, yes. This is the correct term, namespaces. And namespaces is a Linux feature that allows us to gain isolation on several operating system layers. And some of the common layers are the process namespace, the network namespace, the mount namespace. Not working? Still not working? Okay. Okay, the UTS namespace, the user namespace, and last, the IPC, which stands for Inter-Process Communication Namespace. And on the next few slides, I will elaborate more about each of these namespaces and how do they operate. So first of all, we have the process namespace. And as you know, in Linux, when Linux first boots up, the first process that boots up, does anyone know? Init, right? Init, which is PID number 1, we can see it here on the host. And the init process has a significant role in the operating system. It boots up the entire processes later on. And everyone, in the end of the day, is a descendant of PID number 1. When we are talking about process isolation, we are talking about taking a process from the host namespace, from the host process namespace, and certain fake it and make him think that he belongs to a different root of process tree. So if we look on the diagram here, we can see PID 10736. This is an actual process living on the host namespace, on the process namespace of the host. But this process, if you go into this process and type in Linux, who am I? He will believe that he is PID number 1, that he is the init process. But again, it has two terms. From the host perspective, is just like a normal PID. From his perspective, he belongs to a complete new set of processes. And he cannot see any process above it, nor its siblings. And this is true for the second. I deliberately did not use the term container because we did not reach containers yet. This is processes. This is how a process sees itself in the namespaces term. So process 10796 also sees himself as PID number 1 if he creates a new process namespace. So process namespace is the first one of how we create isolation. Okay, the second one is the network namespace. And as you know, network consists of routes, it consists of firewall rules, such IP tables, and it consists of network devices, such as ETH0 or the loopback device. When we talk about separating a process into a different network namespace, we actually say that we'll create for it a different set of routes, different set of firewall rules, and new network devices. So again, on the diagram here, if you take a look on process B view of his network, you can see that he has a new loopback device and an ETH0 device, which both differ from the host. Before continue, does anyone have any questions so far?
So this ETH0 device inside the namespace, is it the same or not the same?
No, this is a completely different device. This is, if we are not talking about VM, think about this ETH0 as a real physical device. And this one, the ETH0 is a logical device. I will have a different slide about networking later on, so I can elaborate more. The host can reach this device, yes. Yes, but the route, but Docker knows how to configure the route tables with Docker Bridge. I will reach it later on, and I will explain how the container reaches has connectivity to the host itself. Okay, let's continue. Next one, we have the mount namespace. So the mount namespace is the view of the process of how its file system looks. So mount namespace gives different set of mounts for the process. The process that belongs to a different mount namespace will not see the same mount point, the same root directory as the host namespace. And besides that, what is done in containers is to change the root directory. So if we take a look on both processes that changed the mount namespace, both of them changed the root directory to a directory on the host that contains, it's not a faked file system, but it's a file system belonging to some kind of Linux distribution. So each one of them points to a file system, and they cannot see anything above it. So they cannot damage the host. They cannot go into /user on the host. They can only see what's beneath the root file system of their own.
This folder 2 in
Yes.
the host is the root.
Yes, yes, it's the root file system of process B. And process 1 is the root file system of process A. The next one is UTS namespace, and UTS mainly talks about the host name of the process. If you go to a Linux machine and you type host name, you will get some kind of host name. Here in the example, I gave an example of an host name of an EC2 machine, which is IP172 something. And if I take a process A or B and I assign it to a different UTS namespace, it means that it will be assigned to a different host name. So typing host name from process A perspective will result in Mongo something, and from process B, Nginx something.
What does UTS stand for?
I don't remember. Don't remember.
Universal time.
Yes, universal thanks. Yes. Good that we have Iran here. Okay, the next one is user namespace. User namespace is pretty significant. It can be confusing, so I will try to explain it as best as I can. So user namespace actually comes in hierarchy. There are namespaces in layers where each one is a parent or child of each other. So on the blue squares, we have the host namespace where we have user ID 0. Who is user ID 0 on regular Linux distributions? Root, right? User ID 0 is root, so process A runs as root, and we have process B and process C that run with user ID 1000. And 1000 is a non-root user. Now, once we create a new user namespace, what we do from the user namespace perspective is we create a mapping. We create a mapping from a user ID range in the child namespace to a user ID range in the parent namespace. So here, process D that was executed by process C has a user ID 0. But user ID 0 on the child namespace is not user ID 0 on the host namespace. Actually, user ID 0 is mapped to user ID 1000. And it will gain the same permissions as user ID 1000. It will not have permissions of a real root. And maybe the next slide will explain it, we'll try to explain it a bit better. So think about it that we start from the top level, and this is the host namespace. We have users from UID 0 to UID 65533, and UID 0, of course, is the root. If we create another namespace, the second layer, we actually do a mapping between user ID 0 to user ID 4999 to users 1000 to 5999 on the root namespace. So again, user ID 0 on this namespace will be equivalent to user ID 1000. And we can go further, up to 32 layers. In the third layer, we have user ID 0, which is actually user ID 1000 in the second layer, which will gain its permission from the permission of the user ID here. It's always going bottom to top. So this is how we gain user namespace isolation in containers.
So on user ID 0 on level 2.
Just a second, I will. Okay.
So user ID 0 on namespace level 2 get user ID 2000 in namespace level 0.
User ID here will be root. It will be equivalent to the user ID 1000 in this level, and it will be equivalent to user ID, let's say 1500 in the top level. From the process perspective, sitting here is root. And when trying to do operations on the file system will enforce the operation based on its policy, on its permissions. And the operating system does not care that is calling him UID 0 root. It will try to go up the layers of the namespace to see who this user really is and what are his permissions. So you will get the permissions from the top level user namespace.
Really same user?
This is the same user, yes. User ID, let's talk about those two. User ID 0 here is user ID 1000 here. If you go to Linux and check your container, and you will go into the container, you will type UMI, you will see root, you will take the process ID, go to the host, and check the user that's running this process. They should be different in case user namespace is active. Okay, let's go on. The last one is IPC namespace. IPC stands for inter-process communication. As you know, in Linux, every two processes can communicate via message queues, via pipes, via shared memory. Those are the types of inter-process communication. And when we create an IPC namespace, we allow processes in the same namespace to communicate with each other via those ways. Processes in different namespaces cannot do it. They cannot use shared pipes or message queues. It's only relevant to the namespace. Okay, so we covered the 6 main namespaces we have in Linux. We have a few more, but I choose to focus on them because they are the most important one. And how do we create namespaces? So the operating system gives us 3 main system calls, which is clone, setns, and unshare. Those system calls receive system call flags. Each flag corresponds to a different namespace. Clone and unshare system calls are very much similar. They both create a new namespace based on the flag given. The difference between them is that clone only creates a new namespace, while unshare also, besides creating the namespace, assigns the new namespace to the calling process. This is the only difference. Setns takes a process, takes a namespace, and assigns them together. And let's see a working example. I try to write a simple Go code that what it does, if you look on line number 12, specify the command that I want to run, which is a simple bash shell, and assigns all the relevant namespace flags. So all that we spoke about, network namespace, IPC, mount, everything is here. And on line number 25, we run this command. And what happens here is that when running this command, we have 2 active processes online. The first one is the main process that ran the command. And the second one is a bash shell. Now the bash shell runs in different namespaces than the main code. You can take the following code, run it on your machine and compare the namespaces, you will see that they differ. And this is, by the way, you can look on it as a very naive implementation of a real container, because we spoke about a container as a process or more than one processor that are completely isolated from the system. And we gained that with, I don't know, 15 lines of code. That's all. We don't need Docker for that. We can use the operating system as is. So how does it look? How do I check which namespace I belong to? If you type in Linux proc self, you get the current process. Proc self ns shows you the mapping of all the namespaces. So again, once this lecture is done, whoever is interested can go and find his Docker process ID, do proc with the PID of the Docker process ID NS, and you will find that it is different from proc self or the shell process that he runs in that time. You will see that the namespaces differ. By the way, not all of them, but most of them differ. And just to summarize, this is how it looks from the process perspective. Imagine that we have 4 processes in the system. 3 processes, if we did nothing, belong to the main namespace, the default namespace, and P4, which is a new process, the one we just created, points to a new set of namespaces. This is the meaning, and again, in the end of the day, there is no real container term. It's just a process that thinks it lives in a different environment. Any questions regarding namespaces? Okay. Okay.
Is those namespace like share, say you can use this amount of memory?
This is our next slide. So you're a bit advanced. We will talk about it in our next slide. So again, so you just said what I'm about to say. There is still one thing missing when we talk about an isolated environment. And the one thing missing is, again, as you mentioned, resources. So, okay, me too, be here. Mom? Okay. I will just repeat, what is your name? Or. I'll just repeat what Or said, or ask if there is a Linux way to say, to limit the resources of the calling process, to say you can use, I don't know, X amount of memory, X amount of CPU. And the answer is yes. And this is what we are going to talk about right now. This is our missing piece for making the containers completely isolated. And again, some trivial questions. Can the container consume all of the host memory in that way? The answer is yes, because it's just a simple process. And can the container consume all of the disk space of the host? Yes. And third question, we can go on with regarding different metrics. The CPU can also be consumed completely. So we need a way to restrict and set limits for our running containers so they will not finish all of the operating system that hosts us. And we need to do it, and the way to do it is by C groups. And C groups is a short term for control groups. Again, it's an old Linux feature. And what control groups actually do is give us a way to limit some of the resources. Among the common one are CPU, memory, storage, and network. Of course, there are many more. We can view them here. If you go to sysfs C group, you can see all the components that can be restricted. And if we are interested in checking the quotas for our running containers, what Docker does is under the relevant directory, it can be CPU, it can be memory, it can be network, it creates a Docker directory with the relevant SHA-ID of the running container, and underneath it you can find all of the restrictions. And again, the operating system knows how to enforce those limits and to kill the container if needed. So it will not harm the operating system, the host. So this is it regarding the first part of cgroup and namespaces. And again, before moving on to the Docker internals, does anyone have any question? Maybe someone on the Zoom? Okay, so I will continue to Docker internals. And this part has three components that I would like to talk about. And the first one are Docker images. And I want to ask you, what exactly are Docker images? Does anyone know the answer? Tar files, okay. More precisely, does anyone know to define them? Maybe someone from Dart team? A cookbook for the container is a very good definition. And the definition that I wrote for myself, which is very close to this, is a Docker image is a template that contains all the instructions we need in order to create a container that runs on a Docker platform. And we'll see shortly how does it look like, but who knows how do we create Docker images? Docker file, right. Docker file is the template upon which we use to create Docker images. And a Docker file, I hope it's big enough, looks something similar to that. It's a very simple application. A Docker file always starts from a from statement. And the from statement takes some kind of image as a base image upon the container can start from. It can be Alpine, as in this example, it can be Ubuntu, it can be Debian, it can be anything you like, but it always has to start with a from statement. And afterwards, you have a bunch of commands that instruct Docker what to do and how to build the image. And how does it look like from behind the scenes? Once we start building this Docker file, we have the terms layers. The Docker image consists of several layers. So the base image is the first layer. Actually, it consists of more than one layer, but for convenience, we'll refer to it as a one layer. And from there, each command that you specify in the Docker file adds a new layer to the final image. So if we look on the final flow of this Docker file, we started from the left side with the base image, and each command, the work there, the copy, the run, the copy, and the command added a layer up to 6 layers with the base image. And those 6 layers will consist of the final image that from this image, the Docker container will be created from. And from the build perspective, this is a snapshot of building a Docker image from a Docker file. So you can see between the first red arrow to the second one, what Docker does is to download the base image, which is Alpine. After doing that, between the second arrows, you can see that it has 2 out of 5, 3 out of 5, 5 out of 5. Those are the new layers added to the final image. And once doing that, he exports the layer, writes the image with a new SHA-ID, which is the bottom line. And this image can be used to run our Docker container. So this is the first part regarding Docker images. the next stop is Docker networking. Someone asked at first, and let's try to explain what's going on in terms of networking. So if you recall, when creating a container, we create a new network namespace. And the new network namespace has its own routes and firewall and network devices, as we said. The only problem with that is that this new container, this new process does not have connectivity to the outside world. It cannot talk to any one of the related containers. It cannot talk to the host. It cannot talk to the internet because it is on a different namespace. So how Docker solves this issue? So apparently there is a Linux feature in networking called vet devices. And vet devices always come in pair. There are like twin devices. The receiving side of when one side transmits packets, the other side receives, and vice versa. And those vet devices were created in order to connect two distinct network namespaces. So what Docker does upon creating a container is create those vet devices. The one vet device, let's call it vet2 in the diagram here. The second vet device sits on the container side where ETH0 is. It's actually a vet device, but Docker changed the name of this vet device to ETH0 because it's more convenient. But it's the second pair, it's the brother of the vet device on the host side. And once we have those two devices, we have connectivity between one network namespace to the other. Now, what else do we miss? We need a way to assign those containers IP addresses, and we need to configure routing for them. And how do we do it? So Docker has many solutions for that. I just wanted to present the most common one that I guess some of you are familiar with, which is the Docker bridge. Docker creates a Docker bridge on the host machine, and every new container added to the system, upon adding those vet devices, it connects the vet device on the host to the Docker bridge. So think about it, that vet number 1 and vet number 2 are connected to the Docker bridge. And each traffic going from ETH0 on the right container goes through vet2 and then to the Docker bridge. And the same one applies for the other Docker on the left side. And the new Docker bridge also has an IP address, and it acts as a DHCP server. DHCP server is a component that knows how to assign IP addresses and knows how to assign DNS configuration. So once we have the Docker bridge on air, and with the vet devices connected, the Docker containers have full network connectivity, both inside the host and outside the host. And from the network perspective, how does it work? Think about a container, the right container that tries to exit to the internet. So the container uses is ETH0 interface, which is again not a real interface. And the traffic goes to vet2. Vet2 is connected to the Docker bridge. The Docker bridge knows how to route the traffic to ETH0 and from ETH0 to the internet. And the flow on the back is the same. Traffic going to ETH0, going to the Docker bridge, to vet2 and ETH0. And from there, the container can handle the traffic. And container to container also works similarly. Everything goes via the Docker bridge, both on the transmit direction as well as the receive direction. And again, as I mentioned, Docker has all kinds of topologies. You can create very complex ones. I think this one is the most common you'll ever face with Docker. What? No, the NAT is performed only for packets leaving the host. Inside the host, there is no NAT. It's bridging.
The host uses a NAT go outside.
Yes, container that wants to go outside will go through here to ETH0, and the packet leaving the container will change its source IP from the container IP to the ETH0 IP, because I didn't mention containers run on private subnet. It's not a routable subnet. So yes, a NAT will occur when containers go outside. Inside the host, they don't need to be NATed because they are familiar with the subnet ranges. They are under the same local network.
How does the traffic coming from the internet know which container?
Because this is a connection tracking feature of the Linux kernel. Once the traffic goes out, it is saved coming in, so you need to define explicitly a rule to which container to forward. But if traffic coming out, Linux saves the way it came out, and it knows for traffic that goes in, how it should manipulate the packet to direct it to the right container.
When it's a host network, does all this happen, or?
When it's a host network, we don't have this ETH0. We have the real ETH0, and everything goes as normal, as if we were on the host.
We can actually trace the virtual port to the real port and get an IP address from the real JTP.
Yes, you are right. If we, yes, Eran, what Eran suggested is it's a bit complex. Okay, so okay, עוד 5 דקות. Okay. Okay, so let's continue. We don't have much time, so I'll try to speak about the last component here in Docker internals, which is the Docker file system. And Docker uses union file system. Does anyone know what a union file system is? Okay, a union file system is a file system that creates an illusion that we have several directories. We see one directory, which actually there are several real directories, but the operating system shows us them as if they were one single directory. And Docker uses some few engines that do it, few storage devices that do it. Among them are UnionFS, AUFS, Overlay, and BetterFS. And we'll try to do it quickly. Does anyone know why Docker choose to use union file system? We have multiple layers, right, and we can share. So think about it that if we have two distinct images that most of their layers are common, instead of creating two containers that duplicate their file system, we can share all the layers, all the common layers, and only the diff part will be different from each container. So the answer is yes. This way we save a lot of disk space by sharing the image layers. And how does it work? So look on the image here. We have in overlay.fs, we have the term lower dir, upper dir, and merged. The lower dir is think about it as the full file system, the base file system, and the upper dir are only the contents of the container that are changed. So the merged dir shows the union of both of them. So if the container layer added file number 4, we will see file number 4 along with file number 1, file number 2, and file number 3 in the merged layer. And let's look on an example. I pulled a Docker image, Nginx, and I inspected the image. And as you can see, the first paragraph is lower dir, merged dir, and upper dir. Upper dir, again, the term is also diff. And if I inspect the real file system of the container layer, I can see that it only changed few files under etc, run, and var. So what will happen with the overlay file system is that it will take the base image of Nginx, the base file system. It will apply this container layer and create for us a merged view of the file system. What I didn't mention is that if we have duplicates in the file system, let's say, for example, I have here /run/nginx speed, and the lower dir also includes this exactly same file, the upper dir gets priority, and the file that will be presented to the user will be the one from the upper dir. So I guess we don't have time, right? Okay, so I will skip the last part. I will try to conclude, although the conclusion includes some few important things from here. Just a second. יש כמה שקפים, לא, אני לא אצליח לסיים. הגיע ל-questions and answers, שנייה. טוב, we'll skip that part. Just everything both. Yeah. So, okay, the summary part includes some contents from the previous slide, but again, if I want to conclude and summarize, we spoke about namespaces and cgroups, which are the building blocks for running containers. And we spoke about the Docker internals, which specify how images are created and what are images, how network is laid out, and how the file system is handled by Docker. And Docker, in the end of the day, we didn't manage to speak about the Docker architecture, but in the end of the day, Docker did not invent the wheel. Docker does not do anything special. Docker just took the capabilities of the operating system, mainly cgroup and namespaces and some more, and created a platform which is very much convenient to use. And this is why it gained its popularity, its big popularity. And I hope I try to convince you that there is no real black magic inside. It's just regular Linux boring commands that create the containers as we know and use. So I will skip this part and skip to the questions and answers. Okay, so we're done. I hope you enjoyed the talk. Does anyone have questions regarding the talk, something that was unclear?
Kernel, you did not mention it, but I think it's worth mentioning. Kernel.
Yes, so I didn't mention it, but of course the difference between virtual machine and containers, virtual machines really work on a different kernel. The containers work on a single kernel, on the host kernel. This is the big difference between them. This is why we share the resources. This is why we need to restrict the resources using cgroups. Yes, good comment. Anything else? Okay, it was nice having this talk. Thank you very much.